The recursive pattern. The recursive pattern means what happened, or why is this? Why does this come from this the two above it in that? Okay. If you think about it in terms of moves on the grid, it's obvious why, right? If you go back here and go back to the thing we counted there, right? So let's go to one that maybe we won't go all the way down to that number, but we'll go back to one here that we already were okay with the fact that this was 1, 2, 1 here. We counted the ways, right? We know there's one way to get here and two ways to get here because we actually drew them, right? There's one way to get there. It's better actually with curves like plunk, plunk like that. And then this one was left, right, or right, left. If there's one way to get there and two ways to get there, if you say how many ways are there to get here, it's pretty obvious why it comes from the ones before, because where are the only places, if it's a ball falling down through here, where are the only places it can come from to get to that square? From the two directly above it. If it's one of those things with little pegs and the ball falls and bounces off either this way or this way, it can only come from the two above it. To get to here, it can only come from the two above it, so it's coming from there or there. Okay? It's like Plinko, yeah, whatever that thing is, right? It all falls down. If you want to know that this is 3 then, it comes from the two above it, because if we're thinking of the physical thing here and it falling down, that's the only way it can happen. This has got to be a 6. If this was kind of streets and you were walking here, if you know there are 3 ways to get to this thing and there are 3 ways to get to this thing, there has to be 6 ways to get to this spot here. If I realize that this is not true, but if you think of there's 2 ways to get in this room, through that door and through that window, even though no one has ever come in the room through that window. If there are 50 ways to come in that door and 2 ways to come, to get here to that window, 50 and 2, there's 52 ways to get in the room, right? Because you add them. Because you can come through that door or that window, right? I just made that up. Well, no, I mean, okay, you could come in that side door and come in here. You could come down the ramp in here. You could come over here. I don't know. However, because there's other things, right? Here you could come through the forest, or I don't know. You could come this way or this way. That's why there's 2. There's 50 and 2. But it's an or, right? Because it's that or that. And when it's or, what do? You add them, right? Because you can't do both of them, right? If any one of these, you either have to come from here or here, so you add those 2 numbers. That's one rationale for why this recursive pattern works. That's why this comes from those 2 added. Here's another way of thinking about this in general terms, in terms of combinations, but not in terms of this. In terms of combinations, we need some space for this. Let's pretend we have 5 people here. We are going to be creative and call them A, B, C, D, and E. We are going to choose 3 of those 5 and shove them out the window. Okay? We're going to choose 3 of those 5. I don't know. We're going to do something with them. If we're actually setting out to choose them, we could just do this and say 5C3. We're going to calculate that, right? And it gives us some kind of number. What does that give us? I think it's 10, but it gives us 10, right? I'm pretty sure. If you actually had to set out kind of writing out the possibilities here for the number of ways we could pick 3 people from those 5, you could split it into 2 cases. Okay? You could start to split it up here. You could say, my first way I'm going to split this up is to say, I'm going to look at this person. Either they're somebody we shove out the window or they're not. So we're going to split it into 2 cases. Either A is in or A is out. Okay? Either they're in the group or they're out. If A is chosen, right? if A is chosen, then what do we need to do to complete our group? Here's our group we're choosing. Here's our 3 spots. If A is part of the group, then what do we need to do to complete our group? You got to pick 2 more from how many? Okay, then you need 2 more from remaining 4, right? From the remaining 4. So in other words, from the remaining 4, you choose 2, right? So I set up here either A is in or A is out. If I count 4C2, that's all the ways that you can count groups where A is included, right? Does that make sense? Or what's the other possibility here? There was this. If A is chosen, then I need 2 from the remaining 4. What's the or here? Or if A is not chosen, what do I need to do? Well, let's say if A is not chosen, how do I complete my group then? I need to pick how many? 3 from the remaining 4, right? Then 3 from the remaining 4, right? Then need 3 from remaining 4. So in other words, from the remaining 4, I need 3. Since that's an or, this is, what do I do with those 2 numbers? This is a plus. This happens to be, this happens to be 6. This happens to be 4. That's where the 10 comes from. You wouldn't do all that, but you guys need, one of the outcomes is students need to understand why the recursive pattern in combinations works. You wouldn't do all that. You would just say, well, if I'm 3 from 5, I have to do that. Sometimes you do have to do this. I mean, the only time you actually have to do cases like this is when you need to work out the cases using a different strategy. Like there's card questions, things we've done that you need the cases are different. You can't do it all at once. You could even keep breaking this down, right? You could say, I just broke down 10 into those 2, because then you could start to say, well, out of my remaining 2 here, either B is a part of the group or they're not a part of the group. And then you could keep breaking it down. You'd get exactly like you'd work your way up through those numbers, right? You'd work your way up through the pattern. You'd say, we have a 6 here and a 4 here, which is this 10. So you'd say, well, either A is in or out. And then if they're out, then either this or this. And so on. You get all the way down. You'd come up with you'd see where all the numbers come from before it. We're not going to do that here because it's going to add up to lots. And I said there wasn't going to be part 5. There are some problems here for you to do. Some of them are silly. What's the 20 millionth term in the 7 millionth row of, well, that wouldn't work, but what's the 182nd term of the 365th row of Pascal's triangle? That's just asking you to make sure you understand the relationship without actually drawing the whole thing. Don't draw down to the 17th row here. Answer it by understanding the relationship. So that's all that stuff. That's kind of the first level of being able to do this. And then there's actually applying it to something, this recursively adding. Think of these as streets and avenues. These are pathway problems. We have done pathway problems that look like this before. We have not done pathway problems that look like this before. Because our method before, we could only use them on these nice square grids like this. But you can apply this concept. I'm here and I want to get to there. I'm going to count the ways, recursively adding to get there. You got to recursively add by breaking it down. If I'm starting here, well, there would be one way to get to there and one way to get to there. There's only one way to get there. I go straight down. That means there's only one way to get to any of those spots. But as soon as I get here, I don't have to count all the paths and say, well, I could get there this way and this way. If I know there's one way to get there and one way to get there, how many ways are there to get here? There has to be 2, because I can just add the previous ones. You think about it and make sure you can even get this one right. And then make sure you don't do something silly like, oh, this is one of those grid things. I just put the numbers on the little lines here. Because you have to think about where you're actually moving and what's happening. This is like roads, and here's you. You're a dot. You're actually moving on the roads. This is pathways on a road. These are roads, right? I'm past 10. I got this is overtime. I always have 30 or 40 seconds of overtime here. You're traveling on the roads here. This is a chessboard. You don't travel on the lines, do you? Where do you travel? The squares. Don't try to do this by memorizing. This is a classic, the memorizer gets this wrong. You want to know why? Because this is how they think. I'm going to have to stop.